Swayam Prabha. Digital India. Educated India.
Last class we looked at the simple problem of conduction in a one dimensional plane wall without heat generation, but we saw very interesting boundary conditions. We saw the case of interesting boundary conditions where you got two fluids at different temperatures T infinity 1 and T infinity 2 on the two sides, which give rise to two different convective heat transfer coefficients H1 and H2, and though the temperature profile was still linear, the algebra was quite involved. It took quite some time for us to figure out the solution. Under the special case of H1 and H2 turning to infinity, then you get the simple case where Q is equal to K into delta T by L, and the temperature distribution is simply that linear temperature distribution which T1 and T2 specified at the ends. Towards the end of yesterday's class, we looked at the problem of the same plane wall with a variable thermal conductivity. The variable thermal conductivity can have two variants. The K can be a function of X and the K can be a function of T. When K is a function of X, we figured out a generic formulation to get the solution, and we wrote it in terms of K of X dx, right, in yesterday's class. So if I tell you, if somebody tells you what the K of X is, that is if it is written as A plus Bx and A and B are specified to you either from experiments or from theory, you will be in a position to calculate the temperature distribution and the heat transfer rate for the case of a variable thermal conductivity, right. So please remember, we are able to work out analytical solutions because it is simple enough and it is only one dimensional and so on. The moment it becomes two dimensional unsteady or three dimensional unsteady and so on, then you have to solve it numerically. Either you have to write your own code or you can take resource to software. Okay. So now we look at the case of variable thermal conductivity where K is a function of T. Okay. So temperature is what you are seeking, that is a solution to the problem, that is a variable. Dependent variable in the problem is temperature and the independent variable is X. Unfortunately, the K, which is the property thermal conductivity, itself depends on T. Okay. Many times K is a function of temperature, therefore variable thermal conductivity is not just an academic exercise, it is an important practical problem. So we will look at a not a very elementary case, but a reasonable linear model for thermal conductivity. So it goes as K is equal to K naught into 1 plus alpha T, right. So if you have done experiments, you got various values of K measured for various values of temperature, you can do least square regression and get the values of alpha and K naught if you have a model like this, right. As you can see, as the temperature increases 1 plus alpha T increases, therefore K is an increasing model for thermal conductivity, right. As temperature increases, K increases, right. Now we will have to get the temperature distribution and the heat transfer rate for a problem in which K exhibits this behavior. We will work out the generic solution, then stop in between, we will put some values for all this alpha, K naught, the thickness of the wall and all that, and get a hang of the whole thing by solving a numerical example before going to a case of one dimensional plane wall with heat generation. So I want to take up two things today: 1D plane wall, variable thermal conductivity, 1D plane wall with constant heat generation rate, which mimics what happens in a nuclear fuel rod. Okay. So let us look at this equation. So we have sometimes I use QV, sometimes I use Q triple prime, so you can be consistent. Okay. So whichever you prefer you use, basically it is watts per meter cube. Now I told you it is steady, so this term gets knocked off. I also told you Q equal to 0, so the two terms get knocked off. Unfortunately I cannot take K out of the differential because K is a function of temperature. Okay. Therefore BC is boundary condition. With the understanding that T1 is greater than T2, right? It can also be the other way. Because please remember, if T1 equal to T2, in this case there is no heat transfer. It is not the case with radiation. They will continue to emit radiation because of Provost's law, but net radiation will be 0, right. So, temperature difference is responsible for heat transfer generally, okay. Why I put generally? Because it is not applicable for radiative heat transfer, okay. So, now we will have to solve this. I can use the linear model for thermal conductivity K. Before using the model, I can just start off with a generic formulation. So, d by dx what is K dt by dx? Heat. Minus of heat flux, correct. I would like to use Q itself and QV for volumetric heat generation rate. Suppose you do not like it, put the double prime so that you are sure that it is watts per meter square, okay. Let us keep it like this. Is that correct? A is a constant, integral dx 0 to L is L, is that okay? People who came late, you noticed we are doing this problem. That is thermal conductivity is varying with temperature, that is a problem we are solving. I am proceeding from 6. So, what can I say about this? A is equal to Q is equal to minus A. I just change T1 to T2. Now it is straightforward. If I know the functional form of K of T, it is possible to insert it into the integral, integrate this and substitute the limits T2 and T1 and we are home. But there is only one part of the story. If somebody says what is the temperature in between at the middle of the slab, or 25% from the left side, 75% from the right side or left side, we are not done yet. But if somebody wants heat transfer rate, we have an answer to that. Now can we say that this is also equal to some mean thermal conductivity Km multiplied by the temperature difference divided by the width of the slab? I am proposing, because it may be very useful from an engineering point of view to define something like a mean thermal conductivity, right, where Did you guys do this in the basic heat transfer course? ME 317 you have not done, people from outside you have done, okay. So now we get an expression for Km. What is Km? Okay. The first step in solving such a problem would be to get the expression for K of t, put it into the integral, evaluate the mean thermal conductivity, and mean thermal conductivity into delta T divided by L will directly give the Q. First part of the problem is over. The second part involves getting the temperature distribution, it is slightly more involved. Is this clear now? Now let us assign some values, otherwise it is getting very dry. So we will assign some values and try to solve this problem. Problem number 40. New notebook, Vikram?
42.
Problem number 42, good. Problem number 42, consider the one dimensional slab given in the figure. Consider the one dimensional slab given in the figure. Okay. So K is 15 into 1 plus 6 into 10 to the power of minus 4 T. Consider the one dimensional slab given in the figure. The thermal conductivity of the slab material varies as K equals 15 into 1 plus 6 10 to the minus 4 into T. Consider the one dimensional plane wall given in the figure. The thermal conductivity of the slab material varies as K equal to 15 into 1 plus alpha into T, where alpha is 6 into 10 to the minus 4 or 10 to the power of minus 4. Okay. The slab thickness L is 50 millimeter. The slab thickness L equal to 50 millimeters. The left side temperature T1 is 600 Kelvin. The right side temperature T2 is 300 Kelvin. So left side temperature is 600 Kelvin, right side temperature is 300 Kelvin. QV equal to 0 and steady state exists in the slab. QV is equal to 0 and steady state exists in the slab. QV is equal to 0 and steady state exists in the slab. For these conditions, determine the heat flux across the wall. For these conditions, determine the heat flux across the wall and the temperature at the mid plane. Determine the heat flux across the wall and the temperature at the mid plane. And the temperature at the mid plane. Okay. We will start solving the first part. Okay. So first get the mean thermal conductivity. correct? Yeah. Now tell me the value of Km. Okay. So Km what is it, Deepak? 19. Ah. 19.05. 19.5. 19.5. Ah. Yeah, 19.05. 19.05 watt per meters per Kelvin. Fine. Now we can substitute in the expression Q the heat flux is the product of mean thermal conductivity into delta T by L. It will be Ajar, quite something, huh? Some kilowatts, huh? 114.3 kilowatt per meter square, correct? 114 point. So it is a reasonable thermal conductivity corresponding to stainless steel, terrific temperature difference of 300 Kelvin. Okay, so we expect a reasonable heat flux of 114 kilowatt per meter square. All right. Okay, but this is not the full story. Okay, the second part is more involved. What is the temperature at the mid plane? That is at x equal to 2.5 centimeter or x equal to 0.025 meter. Okay, so that is going to be a little more involved. Let us see how it. So this is okay up to this. Rohit, it's clear? Kaustubh? The second part of the story is difficult. So we just now evaluated A is a constant, the heat flux is a constant. One dimensional plane wall, no heat generation, steady state, whatever is coming from the left side has to go on to the right side. Okay, where else can it go? So therefore what is the x we want to do? X equal to 0.025 mid plane. Yeah, just get me the right side. Shall we take this fellow also here? Huh? What do you say? Yeah, tell me, what is this? Chetan, right side. Watch out, kilowatt. That's all, everything taken care of. Minus 190.5, very good. If we do not get the final answer, we will catch Vikram. 190.5. okay. Now left side, what about the left side? What is T1? What is happening now to the temperature distribution? You have to solve a quadratic. See, you have a very simple linear temperature distribution. Now, linear temperature distribution, constant thermal conductivity, linear thermal conductivity, quadratic temperature, quadratic thermal conductivity, cubic temperature. It will keep on in the difficulty level will escalate. Now, I hope to get a reasonable temperature, I do not know. So, let us see. So, this is 3 into 10 to the power of minus 4 T square plus T minus 600 minus 3 into 10 to the power of minus 4 into 600 square plus 190.5 equal to 0. Divide throughout by 3 into 10 to the power of minus 4 and make it into a decent quadratic equation. What do you get? 4? Very good. Okay, now let us write the quadratic. Minus what is the quadratic? There is a provision in the calculator, is it? But what is it? What is the C term? 5
That is divided by 175.
Some Ajar. 1 point?
455 10 power 6.
On solving? T mid is 0.3. What is the big deal, man? The layman who has no knowledge of heat transfer will try to guess that it will be 600 plus 300 by 2, but it is off by 5 Kelvin. You may say, what is there in 5 Kelvin? But suppose the K and the variation of K is much more severe and the two temperature differences are too much, then the layman approach will not work. You cannot simply take the arithmetic mean temperature difference and say that, because there is a physics associated with this problem. You should know the physics in order to get this. Are you getting the point? Therefore, this is 600, this is 300. Okay, 450, 600, 300. What did we get at the center now? Slightly more than this. Okay, so a linear model for thermal conductivity gives rise to the yellow line. A linear model can also give rise to the orange line. The yellow line is for alpha greater than 0. This is for alpha less than 0. Thermal conductivity can also decrease with temperature, right? This funda is clear. The beauty is the linear temperature profile is disturbed Now we have a quadratic or a parabolic temperature profile. It is consistent with the linear model for thermal conductivity, right. Alpha equal to 0 gives the linear model, fine. We got it numerically, we can also explain it intuitively, okay. Watch here, since the temperature is the difference is the same, for a given heat flux for a linear temperature profile there is a temperature gradient here. To transfer the same amount of heat at a higher temperature, if alpha is greater than 0 the thermal conductivity is more. So Q is equal to k dt by dx, because Q is the same and k is more, the dt by dx must be lesser, it must be gentle for the case where alpha is greater than 0. By the same token, for the same Q, if alpha is negative then the k corresponding to the constant k model has to be lower, therefore the dt by dx has to be correspondingly higher to make up for the constant heat flux case. Suppose I had told you like this, you may or may not believe me, that is why I took a detailed this thing where we numerically solved and I proved that for alpha greater than 0 the mid plane temperature will be always higher than what is predicted by the arithmetic mean temperature difference, okay, right. So once linear we can have a quadratic fit for thermal conductivity and all this. So now you know way of handling this, right, and oftentimes for large variations in temperature this constant thermal conductivity model is no good. If the temperature difference is small, it is alright to use this, okay. Now let us take the 1D plane wall with heat generation. The heat generation can take place because of a nuclear fission or it can take place because of a chemical reaction and so on. So consider a plane wall like this, okay. So it is infinite in extent. Now I have a material which has a constant thermal conductivity K, let us not complicate it, but now I have a fellow who is generating heat at the rate of QV watts per meter cube. But to make matter simple, I am taking it infinitely deep in the direction perpendicular to the plane of the board, volume will be L into 1, okay. Now for convenience I am starting x from here, please look at the board, I am starting, origin is here, so this is L, this is also L, the slab is of thickness 2L. If I leave him like this, what will happen without anything on the boundary? If it is both sides are insulated, what will happen? He is continuously generating heat, temperature will increase, no steady state will be reached. Therefore, I am cooling it on both sides, I am bathing it with a fluid, the cold fluid which has a temperature of T infinity and which gives a heat transfer coefficient of H. Suppose I have a fan or a blower or a pump which will pump the liquid, it has to be continuously removed, otherwise I am in trouble, okay. So I have H, not H1, H comma T infinity on both sides. So is the situation clear? Now I want to find out what is the total heat which is transferred in this situation, number 1. Number 2, what will be the temperature at the surface, at the interface between the solid and the liquid, and most importantly what will be the maximum temperature anywhere inside the solid and whether the maximum temperature anywhere in the solid respects or obeys the design limits, okay. So the sodium can, in a nuclear reactor, you will have a lot of fuel rods like this, right. If you look at the top view, one of this top view, so there will be what are called hexagonal fuel sub-assemblies, it is called SAs. Each of these hexagonal fuel assemblies there will be lot of circular tubes, they will be sheathed, like that you will have several hexagonal assemblies, okay. There will be small gaps in between these tubes and there will be gaps between these two hexagonal subassemblies. So that is called the inter-wrapper distance. Then there will be, because packing density cannot be 100%, there will be some gap in between. So the sodium will flow from bottom to top. I am talking about sodium because the Indian reactor is sodium. So bottom to top the sodium will flow, it will pick up the heat, then it will go to a heat exchanger, then there is secondary heat exchanger where secondary sodium will pick up the heat from the primary sodium, it will get heated, then at the third stage this sodium will transfer the heat to the water, water will become steam and then it becomes a regular Rankine cycle, okay. Now this pumping of sodium, this is the primary place where the fission heat is taken away from by the sodium. So this heat transfer process is accomplished by the sodium pump. In the event of a tsunami or earthquake or in the event of a station blackout, this pumping system will fail. When this pumping system fails, the high values of H which you got with forced convection will suddenly go down. Then what happens is this temperature will dramatically increase. Alright, if immediately after there is a station blackout, there will be operators who will ensure that control rods are lifted and so that the reactor goes to subcritical conditions. But it is not like this, if you switch off this light it will go, but nuclear reaction is not like, there is a half life, it will continue to generate heat for the next 24 to 48 hours, it may not be at critical conditions, therefore it at a reduced power fission heat will continue to be generated. Now in the absence of a pump, can natural convection sustain? Temperature will no doubt increase, but it should not increase to a level at which it leads to what is called the core meltdown temperature. When the core meltdown takes place, here they have all this, they will have all this what is called the core catcher plate made of stainless steel. Once it is so hot, it will just penetrate, it will just make a hole and go deep and then it will invade the soil and get in. Once it goes in, then it will horizontally spread, it will enter all your aquifers, this thing, it will enter the water, this thing, then with lethal radiation doses everywhere. So this core meltdown is what everybody is afraid of, okay. So ultimately it is the nuclear reactor, whatever happened in Japan is a heat transfer problem, it is a heat transfer, your inability to transfer heat led to all this. So heat transfer can be very, very critical, okay. Now let us do this. So this is 1D, T is a function of constant QV, then K is constant. Okay. Now okay, so rho Cp steady state, steady state, which term can be knocked off? Left side, okay. So we have got so this will be the equation if the fuel rod is basically infinitely deep in the other direction. For one fuel rod, what is the temperature distribution inside the rod subject to the convective boundary conditions outside, okay. So can we integrate it twice? Integrating once, correct? Is it correct? Now you will be easily able to see why I took the x equal to 0 at the center. At this, do you expect a symmetric temperature distribution about the center? If you have a symmetric temperature distribution around the center, dt by dx at x equal to 0 has to be 0. Therefore, which term will get knocked off here? A is 0, okay. At x equal to 0, okay. So, T QV x squared. How will I get the B? How do I get the B? What boundary condition? Convective boundary condition, you can apply minus k dt by dx at x equal to 0, x equal to minus L or x equal to plus L will be equal to
H into H.
okay. But I have a simpler way of doing it. Whatever heat is generated by the fuel rod must be taken away by the fluid, okay, by energy balance. What is the heat which is generated by the fuel rod? QV into 1. 2L is the thickness, 1 is this, okay. Watts per meter cube, meter square, watts. This will be equal to H into H into 2 into 1. Into what is 2 into 1? 1 is this 1 meter square, 2 is left side, right side. Okay, so okay, so can I get the H is known, QV is known, can I get TL straight away? Yeah, but fine, but instead of doing mathematically I am doing physically. If you apply the boundary condition also you will get the same thing. That boundary condition is energy balance, isn't it? Right? Yeah. So, what is this? TL will be equal to T infinity plus QV okay. Comparing 6 and 8. This is the fine, right? So, this is known to us, plus B, right? Is that correct or I am making a mistake? Is it okay? Therefore, T is equal to minus QV x squared by 2k plus TL plus what are the units of this? Watts per meter cube, meter square. So numerator is watts per meter, this is watts per meter per Kelvin, therefore the unit is Kelvin. So this is something called the reference temperature excess, the reference temperature difference for the problem. This gives you the power of the heat generation to increase the temperature inside the wall. Correct? This is called the temperature excess parameter. So easily it can be seen that at x equal to 0, the temperature is maximum. At x equal to L, this term becomes 0, T is equal to TL, that is already you know. What is TL? TL comes from the energy balance. Okay, let us solve an example. Problem number 43, consider a 1D plane wall with constant QV. Consider a 1D plane wall with constant QV. Okay. Consider a plane wall with a constant QV. All the pertinent details are shown on the figure. All the pertinent details are shown on the figure. All the pertinent details are shown on the figure. Determine A. All details shown on figure. Determine A, surface temperature, and B, center temperature. Okay. This is representative, these are not the actual values encountered in a nuclear reactor. I did not choose to give an example, but this will give you an idea. Now you can get TL equal to T infinity plus QVL by H, right, that is what we got. How much is this? Huh?
500.
500 Kelvin. 300 plus 200, huh? Deepak, you use 0.04, that is not correct. 0.04 is 2L, L is 0.02, right? Okay. Now, T center equal to 500 plus what is T center? 506 point. So what does it show? This fuel rod or whatever is generating heat, you are having a cooling medium which affords a heat transfer coefficient of 50, which is available at 27 degrees centigrade 300 Kelvin to do the cooling. So the conduction is better, that is why from the surface to the center the difference is only 6.67 Kelvin. But there is a mismatch between the heat generation and the capacity to absorb the heat by convection, that is why from 300 the temperature rises to 500. So a temperature difference of 200 degrees centigrade is required at the surface in order to accomplish the heat transfer. But now let us take a situation, now let us say this is forced convection, the Fukushima reactor whatever, these are all representative value. Let us say from 50 because of natural convection it suddenly drops to 5, what happens? If H drops to 5, how much is TL? Huh? What will happen to the fuel rod? Do not worry about one dimensional governing equation inside the rod, at the surface itself cups. This is what happens where if the pumps fail. Of course we assume lot of things, steady state and all that, but this will be the starting story. Immediately some operator will put control rod, you will put boron, something they will do all that. But immediately the first thing is there will be a thermal shock, right? The H drops and suddenly the fuel rod temperature they will start rising like mad. Okay, fine. We will stop here. In tomorrow's class we will look at extended surface heat transfer, that is fins.